Hello everyone, welcome to this lesson. My name is Stephen Ouru. I'll be taking you through a unit of competency, apply electrical principles. And today we are going to look at capacitors and capacitance. So before we start, let me confirm the presence of these people. Phineas Munene, Ken Sati.
Present.
Okay, I can see you around. So without further ado, let me share my screen. Okay, as I said, we are going to look at capacitor and capacitance, and these are the outcomes. So by the end of this session, I'm expecting you to be able to define the term capacitor. These are the learning outcomes that I'm expecting you to know by the end of this session. You don't see this? Hello? Are you seeing what I'm sharing? Okay, so these are the learning outcomes. Number one, define the term capacitor. Number two, state Coulomb's law of charges. Number three, perform simple calculations using Coulomb's law. Number four, describe electric field intensity. And number five, define capacitance and state its SI unit. So what is a capacitor? This is just electrical device that is used to store electrical energy. And apart from resistor, it is the second most commonly encountered component in electrical circuits. They usually come in different types and shapes, as you can see. As you can see, this sample, these are not the only one. We have different types. We have electrolytic, ceramic, and some other type. So some of the applications of capacitors include smoothing rectified AC outputs. They are usually used in telecommunication systems, tuning receivers, time delay circuits, electrical filters, oscillators, and in magnetic resonance imaging. So now, let's state Coulomb's law. So we already know that if we have two charges, the law of charges states that like charges repel while unlike charges attract. So when two charges are brought close together, a force of attraction or repulsion acts between them. And the strength of that force is given by Coulomb's law, which states the force of attraction or repulsion between two electrically charged bodies is proportional to magnitude of their charges and inversely proportional to the square of the distance separating them. And as you can see, force is directly proportional to Q1, the product of Q1 and Q2, but inversely proportional to the distance d squared. So we can say that F equals to K multiplied by the product of Q1 and Q2 over R squared. where K is a proportionality constant and usually is approximately 8.988. It is a constant. Yes. So let's see one example here of how we can apply this Coulomb's law in solving some problems. Let's see this example here. A point charge of positive 3 times 10 power negative 6 Coulomb is 12.0 centimeter distant from a second point charge of negative 1.50 times 10 raised to negative 6 Coulomb, and we are required to calculate the magnitude of the force on each charge. As you can see, we have a positive charge and a negative charge, so we expect the force of attraction. So being of opposite signs, the two charges attract each other, and the magnitude of the force is given as shown. So F equals to K Q1 multiplied by Q2 over R squared, which if we plug in the constant, which is approximately 8.99 times 10 power 9 multiplied by 3 times 10 power negative 6, we multiply by 1.5 times 10 power negative 6, and then we divide by 12.0, we change it into meter, then we square it. And you can see that we've dropped the negative charge on Q2 because we already know that the force is attractive, so that the positive one will be moving towards the negative one. What we are busy here with is the magnitude, which is always positive. And if we do this, we get 2.81 Newton. I hope we are together.
Yes.
Fine, that's fine. So let's look at electric field intensity. So we realize that if two parallel metal plates, let's say A and B, are charged to different potentials, as shown in this diagram here, an electrostatic force acts between them according to Coulomb's law, as we already seen. The region or space between the plates or point charges, if they are point charges, where that force acts is what is a region we call electric field, and the intensity or the strength of that force per unit distance is what we call electric field intensity. In this case, in our diagram here, electric field intensity, denoted by E, capital E, is given by the potential difference between the two plates, represented by V. Then we divide by the separation distance, the small d. So let's see what capacitance is. We already saw what capacitor is. Now let's see what capacitance is. So static electric fields arise from electric charges where electric field lines are beginning and ending on electric charges. They usually begin. Can you mute, please? They usually begin on the positive charge and end on the negative charge. Thus, the presence of the field indicates the presence of equal positive and negative electric charges on the two plates. So if we say positive Q coulombs is a charge on one plate and negative Q coulombs is another charge on another plate. So now the property of this pair of plates, which determines how much charge corresponds to a given potential difference between the plates is what we call capacitance. In other words, capacitance is the ability of a system of electric charges to store energy. So capacitance in this arrangement is given by this formula here. Capacitance C equals to charge Q, we divide by the voltage or the potential difference V. And the unit of capacitance is the farad, which is defined as the capacitance when a potential difference of 1 volt appears across the plates when charged with 1 coulomb. And the unit is farad, that was given after the name of famous scientist Michael Faraday, who did a lot of research in this field. So now, having gone through all this, now I want to give you an assignment which you can attempt, and we'll look at it in our next lesson. And the assignment is this: what must be the distance between point charge Q1, which is 26 microcoulomb, and point charge Q2, which is negative 47 microcoulomb, for the electrostatic force between them to have a magnitude of 5.7 Newton. So please attempt this. We'll look at it in our next lesson. So thank you very much for attending this lesson. Thank you. Welcome, welcome.